Let's think about how we can define matrix addition. And mathematicians could have chosen any of an arbitrary number of ways to define addition, but they've picked a way to define addition that seems, one, to make sense, and it also has nice properties that allow us to do interesting things with matrices later on. So if you were one of these mathematicians who are first defining how matrices should be added, how would you define adding this first matrix over here to the second one? Well, the most common sense thing that might have jumped out at you, especially because these two matrices have the same dimensions. This is a 2 by 3 matrix, has 2 rows and 3 columns. This is also a 2 by 3 matrix, 2 rows and 3 columns, is to just add the corresponding entries. And if that was your intuition, then you had the same intuition as the mathematical mainstream, that the addition of matrices should literally just be adding the corresponding entries. So in this situation, we add 1 plus 5 to get the corresponding entry in the sum, which is 6. You can add negative 7 plus 0 to get negative 7. You can add 5 plus 3 to get 8. You can add, and I'm running out of colors here, you could add 0 plus 11 to get 11. You can add 3 to negative 1 to get 2. And you could add negative 10 plus 7 to get negative 3. And if you see this definition of matrix addition, you see that it actually does not matter in what order that we actually add these matrices. I could have done this the other way around. If I did this the other way around, let me copy and paste this. So if I were to add this matrix, so let me copy and let me paste it. If I were to add it this way, that matrix to, let me copy and paste the other one, to this matrix. So copy and paste. If I were to go this way, you'll see that the order in which I'm adding the matrices does not matter. So this is just like adding numbers. A plus B is the same thing as B plus A. What we'll see is that this won't be true for every matrix operation that we study. In particular, this will not be true for matrix multiplication. But if you add these two things, using the definition we just came up with, adding corresponding terms, you'll get the exact same result. Up here we added 1 plus 5 and we got 6. Here we'll add 5 plus 1 and we'll get 6. We get the same result because 1 plus 5 is the same thing as 5 plus 1. Here we had 0 plus negative 7. You get negative 7. So you're going to get the exact same thing as we got up here. So when you're adding matrices, if you were to call this matrix right over here matrix A, which we normally denote with a capital bolded letter, and you call this matrix right over here matrix B, then we take the sum of A plus B, which is this thing right over here, and we see it's the exact same thing as matrix B plus matrix A. Now let me ask you an interesting question. What if I wanted to subtract matrices? So let's once again think about matrices that have the same dimensions. So let's say I'm going to have two 2 by 2 matrices. So let's say it's 0, 1, 3, 2. And from that, I want to subtract negative 1, 3, 0, and 5. So you might say, well, maybe we just subtract corresponding entries. And that indeed is how you can define matrix subtraction. In fact, you don't even have to define matrix subtraction. You can let this fall out of what we did with scalar multiplication and matrix addition. We could view this as the exact same thing as taking 0, 1, 3, 2. And to that, we add negative 1 times negative 1, 3, 0, 5. And if you work out the math, you're going to get the exact same result as just subtracting the corresponding terms. So this is going to be, what is this going to be? 0 minus negative 1 is positive 1. 1 minus 3 is negative 2. 3 minus 0 is 3. 2 minus 5 is negative 3. And you'll see that you get the exact same thing over here. When you multiply negative 1 times a negative 1, you get a positive 1. Positive 1 plus 0 is 1. Negative 1 times 3 is negative 3. Plus 1 is negative 2. Fair enough. There might be a question that is lingering in your brain now. Okay, Sal, I understand. When I'm adding or subtracting matrices with the same dimensions, I just add or subtract the corresponding terms. But what happens when I have matrices with different dimensions? So, for example, what about the scenario where I want to add the matrix 1, 0, 3, 5, 0, 1 to the matrix So this is a 3 by 2 matrix, and I want to add it to, let's say, a 2 by 2 matrix. 5, 7, -1, 0. What would we define this as? Well, it turns out that the mathematical mainstream does not define this. This is undefined. This is undefined. So we do not define matrix addition or matrix subtraction when the matrices have different dimensions. There didn't seem to be any reasonable way to do this that would actually be useful and logically consistent in some nice way.